We're going to look at the specific equations known as the roots of unity equations. Arises from when you have z to the power of n equal to either 1 or minus 1. So the modulus is 1. So as I say, those solutions are known as the nth roots of unity. And they would all be plotted on the unit circle, because as I say, the modulus is 1. And remember I talked before about being symmetric around the circle? So you'd get a regular polygon if you were to join them up. So let's look at this one, for example. Z to the power of 5 equals 1. Now I could use de Moivre's, and we'd get cis 2 pi k, well, plus 0, divided by 5. I know they're going to be in conjugate pairs because 1's a real number. So I'll go 0 plus or minus 1 plus or minus 2. And so there they are. Cis 0, 2 pi 5 minus 2 pi 5, 4 pi 5 minus 4 pi 5. And if we plot them, there's our first one, and we're going around every 2 pi and 5. So there's 2 pi and 5, the conjugate must be there. Then 4 pi and 5, the conjugate must be there. Sure enough, we join them up, there's our pentagon, sitting on a nice circle. Oh, hang on, before I move on. A bit of debate with this one. If they were to say, write your answers in mod arg form, and of course one of the answers is 1. And I suppose technically you should really write that as cis 0, because 1's not in mod arg form. Cis 0 is. So just depends. I mean, if they don't ask you to put it in mod arg form, then yeah, you're probably going to just write 1 as the answer. Okay, so same equation, although rearranged. It's z to the power of 5 minus 1 is equal to 0. They're telling us that omega is a complex root. So when they say a complex root, they mean the one that's not real. So it wouldn't be the answer 1. Show that omega squared, cubed, power of 4, and power of 5 would be the other ones. Now they're not telling you which one of those complex ones, because it would be really easy to just say, oh, well, okay, look, let's say it's 2 pi and 5, and then I can create the other ones. But the comeback on that is, well, what if it's not 2 pi and 5? What if that complex root was 4 pi and 5? Would it still work? So we can't tell which one it is, and we're not going to assume it's any of them. So z to the 5 equals 1. All I know is omega is a solution. Now, if that's true, then omega to the power of 5 is 1. But hang on a sec. Omega to the power of 5 to the power of 5 then would be 1 to the power of 5. And 1 to the power of 5 is 1. So it satisfies the equation. So if omega is a solution, omega to the power of 5 must be a solution. Just playing with index laws there. But hang on a sec. Omega squared to the power of 5. That would be the same as omega to the power of 5 squared. And we know omega to the power of 5 is 1, and 1 squared is 1. So omega squared must be a solution. Omega cubed to the power of 5 I could rewrite as omega to the power of 5 cubed. And omega to the power of 5 is 1, and 1 cubed is 1. So therefore omega cubed must be a solution. Omega to the power of 4 to the power of 5, I could write as omega to the power of 5 to the power of 4. But omega to the power of 5 is 1. 1 to the power of 4 is 1. Omega to the power of 4 is a solution. So if omega is a solution, doesn't matter which one I pick, then squared, cubed, fourth, and power of 5 will also be solutions. It won't work for the real one. Because if omega is 1, the only other solutions I'll produce, 1 squared's 1. 1 cubed is 1. Well, so you just keep getting the same answer each time. So that's why it has to be one of the complex ones for this to work. Okay, another way of showing this. We know z to the power of 5 equals 1 if we rearrange our equation. So if omega is a solution, then omega to the power of 5 is equal to 1. So it starts off the same way. Hang on, if k is an integer, then omega to the power of k to the power of 5 will equal omega to the power of 5 to the power of k. Well, in fact, it's true even if it's not an integer, but I'm more interested if it's an integer. So 1 to the power of k, well, that's always equal to 1. So there I get straight away. Rather than having to go through each individual one, I'm generalising and say, well, let k be an integer. So in fact, omega to the power of 6 is a solution, 7 is a solution. Omega to the power of anything is a solution for this equation. So let's prove that if we add up 1 plus omega squared plus omega cubed plus omega 4, we'll get 0. Okay, different ways of thinking about this. They're the roots. Remember, we just found that if omega is a solution, so is squared, cubed, 4, 5. So they're the roots. So I can say, well, the sum of the roots is minus b on a. Well, our equation, z to the power of 5 minus 1 equals 0, b is 0. And the other thing I can say is, well, I know omega to the power of 5 is equal to 1. So therefore, 1 plus omega squared plus omega cubed, power of 4 must equal 0. That's one way we could do it. Another way we could do it, omega to the power of 5 minus 1 is equal to 0. I could factorise that. And we know that will be omega minus 1 is one factor. Then the powers of 1 are going up by 1. The powers of omega are going down by 1. Oh, other way around, isn't it? So I got it wrong. But anyway, you get 1 plus omega squared and so on in the second one. A reminder, omega to the power of n minus 1 is always factorise omega minus 1. And then it's plus all the other powers. We know that omega minus 1 can't equal 0. Remember we said omega was not equal to 1. That's the solution it's not. Therefore, it must be the other factor that's equal to 0. So the 1 plus omega squared and so on. So because we know omega can't equal 1. By the way, if it did equal 1, this would not equal 0. What would it equal? Yeah, because each one is going to be 1. Or, here's another one. So all right, 1 plus omega squared plus omega cubed plus omega to the power of 4. You know what we got? We got a geometric there. We can say the first term is 1, the ratio is omega. And there's 5 terms. So I can put it into our formula for the sum of geometric. That's got to equal 0 because on the top of the fraction we've got omega to the power of 5 minus 1 is equal to 0. There actually is, did I put it down? I don't know if I did. There actually is another way. No, there's another way. If we use vectors, each one of these is a vector, we could say, hang on, we've just added up all of the vectors for 1, omega squared and so on, and it's made a closed shape, so all those vectors must add up to equal 0. So that's another way we could do it. So we're now going to find the quadratic equation with solutions omega plus omega to the 4 and omega squared plus omega cubed. Grouped in that way for a particular reason, by the way. But anyway, some of the roots of our new equation will be omega plus omega 4 plus omega squared plus omega cubed. We know 1 plus omega squared plus omega cubed plus omega 4 is 0. Therefore, that must equal negative 1. Okay, product of the roots. Omega plus omega 4 times omega squared plus omega cubed. If we expand the whole thing out, we get omega cubed plus power of 4, power of 6, power of 7. But remember, omega to the power of 5 is equal to 1. So I can rewrite that. Omega to 6 is the same as omega. Omega to the 7 is the same as omega squared. And we have, yet again, the same thing. Omega squared cubed 4, which is negative 1. We know our quadratic will be minus the sum of the roots. Right. So we'll end up with x squared plus x minus 1 equals 0. I said there's a reason why those are grouped together. Omega and omega to the power of 4 and omega squared and omega cubed are conjugates. The conjugates, the powers should add up to give you whatever the power is. So if you match omega with omega 4, you get 5 added together, so they should be the conjugates. Yeah. And that's why we end up with real numbers here in our equation. Okay, if omega is a complex cube root of unity, so it's a solution to z cubed is equal to 1. They're not going to get us to prove it this time. They're just going to say, look, use the fact that 1 plus omega squared is equal to 0. Find this, 1 plus omega squared cubed. It really is, but a bit of fun with it. Because, yeah, sure, you could cube the whole thing, but you can turn 2 terms into 1. Because 1 plus omega squared is minus omega. And cube that, you get minus omega cubed, so the answer is minus 1. You get fractions like this. Rather than do it in algebraic fraction with 2 terms in each denominator, we can do it with 1, because 1 plus omega is minus omega squared. And 1 plus omega squared is minus omega. And we end up with minus 1 minus omega, and the common denominator is omega squared. But minus 1 minus omega would be omega squared. And so we end up with 1. Remember, we're playing with roots of unity. It's no surprise we're getting a lot of answers that are 1 or minus 1. So which cubic equation would have the roots 1, 1 plus omega, and 1 plus omega squared? We know 1's a solution, so I know there's a factor z minus 1. So I've just pulled that out. That gives me a quadratic inside. So inside the quadratic, the roots are 1 plus omega squared, we know, minus the sum of the roots plus the product. So the sum of the roots, 2 plus omega squared. The product of the roots, 1 plus omega squared plus omega cubed. That gives us z minus 1, z squared minus z plus 1. Because we know 1 plus omega squared is 0, and omega cubed is 1. So the constant's 1. In the second one, I've got 2 plus omega squared, but 1 plus omega squared is 0. So that must equal 1. And if I was to expand the whole thing out, there it is. Z cubed minus z. Oh no, it goes further, doesn't it? Look, those some like terms. Oh look, you get a lovely symmetric thing. Z cubed minus 2z squared plus 2z minus 1 is equal to 0. Solve this equation. Before now, this would have been a bit of a challenge. A pentic equation to solve. So because it's a challenge, I'm not going to do it. I'm going to remember this. Well, z to the power of 6 minus 1, if I factorised it, it would be z minus 1, and then the other factor would be all of those terms added together. Why do that? Well, I can find the solutions to z to the power of 6 minus 1 very easily. They've got to have the same solutions, because the factors of this second one here will be the same as the original equations. All I know is I won't have the answer z equals 1. Yes. So this equation here, z to the 6 minus 1, it will have the answer 1. But if I get rid of that one, I'll be left with all the answers to the other factor. Again, conjugate pairs, so I'm going with 0, plus or minus 1, plus or minus 2, and 3. So that's what I'm trying to solve. Essentially, this is what I'm doing. I'm multiplying top and bottom by z minus 1. And that's why 1's not a solution, because you can't have 1 on the bottom, or 0 on the bottom of the fraction. So I know, yep, solutions to z to the power of 6, but not including the solution z is 1. So we've got cis pi on 3, minus pi on 3, 2 pi on 3, minus 2 pi on 3, and pi. And those ones are all exact values, so I can come up with a much more impressive looking solution. Yeah. Half plus root 3 on 2i, etc., etc. Here's a very old HSC question. This time, they told us the specific one omega is going to be. So it is going to be that smallest one, the 2 pi on 9 for this. So show that omega to the power of k is a solution. Okay. Z to the power of 9 is equal to 1. We know cis 2 pi k on 9, where k is, well this time I just wrote them out. 0, 1, 2, 3, 4, 5, 6, 7, 8. But I can rewrite that using de Morgan's theorem as cis 2 pi on 9 to the power of k. And they told me cis 2 pi on 9 was omega. So z is omega to the power of k, where k is an integer. Prove that all of this is negative 1. Well, essentially, it's exactly the same question again. They're just trying to trick us. It didn't work. By putting the 1 on the other side of the equation. So instead of saying 1 plus omega squared, etc. is equal to 0. So which way did I go for it? Sum of the roots?
Yeah.
I did. Sum of the roots are equal to 0. Move the 1 to the other side. There we go. Hence show that when I multiply these three things together, we get 1/8. Okay. There it is, factorised. Z minus all the individual roots. But you'll notice I've written them not going up in order, which you might expect. Again, I've grouped them, so when you look at the pairs, you get 9. The first one I've left by itself, but then 8 and 1, 9. 2 and 7, 9. 6 and 3, 9. 5 and 4, 9. Because I know that they are conjugates. Now the first one we know is cis 2 pi on 9. So when I expand those two factors out, I will get twice the real part. So cos, and this is where you've got to be careful. It's now cos, not cis. So it's 2 cos 2 pi on 9z plus Well, the product of the roots is going to be 1 because we're playing with the roots of unity. It always turns out. But also because your conjugates are going to multiply together to get the modulus squared, and the modulus of this is always 1. The second one is cos 4 pi on 9. Then we get 6 pi on 9 and 8 pi on 9. All right, and what do we got to get? We want to get these 3 things multiplied together. I've got things multiplied together. Problem is, in these factors, I got this z squared and 1. How could I make them go away? If only there was a number I could substitute in for z. Tell you what, there is, but I'm going to keep you in suspense because look at this one here. It's that one, isn't it? 6 pi on 9, yeah. 6 pi on 9 is an exact value. So I actually worked that one out there to get z squared plus z plus 1. But anyway, let z equal I. We now have I to the power of 9 minus 1 is I minus 1 times, well, the z squared plus 1 is 0, leaving me with minus 2 cos 2 pi 9 I. The next one, 4 pi on 9 I. Next one, cos 8 pi on 9 I. Aye, Capitan. Now, but my z squared plus z plus 1, that's the I sitting there by itself there. But we now have the causes multiplied together. All right, so that's where we got it to. I to the power of 4, because we've got I in the last factor, I by itself, I in the third last factor, I in the fourth last factor. So they all multiply together to give I to the power of 4. We've got, I factorised out the negatives. So negative times negative times negative, that's all negative. So I'll pull the negative out the front. And I to the power of 9 minus 1, well, I to the power of 9 is the same as I. So we got I minus 1. That's good. That's going to cancel with that. So, now I've gone 2 times 2 times 2, 8. The I minus 1 cancels with the I minus 1. The minus I to the power of 4 is negative 1. Multiply both sides by that. Almost there. Oh no, because, oh yes, they didn't say cos 8 pi on 9, they said cos pi on 9 in their multiplication. But cos of 8 pi on 9 will be the negative of cos pi on 9. Second quadrant and the acute angle. Whoops. And so there we have it. Finally, there it is. Approved we're equal to 1/8. Remember I said it was an old one now, but that was nature C.